Hello, my name is Marzoughi. I'm a fourth-year PhD student in CPES, and today I'm going to talk about my most recent project, which is on investigation of impact of medium voltage silicon carbide MOSFETs on medium voltage high-power industrial motor drives. So the objective of this work is to investigate impact of medium voltage silicon carbide semiconductor technology on medium voltage high-power motor drives. For many years, silicon-based semiconductors have been the solution for power electronic applications, including the motor drives. But it seems like the silicon semiconductors have been hitting their limits in blocking voltage, operating temperature, and switching performance. Since their introduction and thanks to their outstanding material properties, the wide bandgap semiconductors such as silicon carbide and gallium nitride have been pushing the operating limits of previous semiconductor generations in operating voltage, switching frequency, capability, and operating temperatures. The aim of us in this project is to first characterize the state-of-the-art 3.3 kV 400 amp non-commercialized full silicon carbide MOSFET, which is granted to us by our sponsor company, Sumitomo Electric Industries of Japan, and then use its data for evaluating motor drive topologies in medium voltage and high power. For driving such a MOSFET, we needed to design a specific gate driver, since the commercial gate drivers, when it comes to silicon carbide at medium voltage and such high current, they hit at least a few of the listed restrictions. So either the isolation voltage of the gate driver or its gate driving current or the embedded protections or DVDT immunity or the footprint can cause us problem. So we have designed a gate driver whose most important specifications are shown in this table. Also, DSAT protection, soft turn-off, active Miller clamping, over voltage and under voltage lockout protections are also embedded on the gate driver. This figure is showing the gate driver mounted on top of the device under test. Having the gate driver designed for characterization purpose, we have used the static characterization using the B1505 curve tracer. Also for dynamic characterization, we have made a setup which includes bulk capacitors, superconductor copper bars, and a hot plate, which is used to take the device under test for high temperatures, for doing high temperature tests. So for dynamic characterization, the gate resistance, junction temperature, and the load current are swept for a wide enough range to extract the dynamic performance of the device under test. Finally, having the test results, we have tried to compare the design and then compare the cascaded edge bridge, modular multi-level converter, and the 5-level active neutral point clamped topologies for industrial motor drives at 4.16, 6.9, and 13.8 kilovolts and 3 and 5 megavolt amps. And we have selected so many voltage and power levels so that we can find the breaking points for each topology or the semiconductor technology. We have done the design using conventional silicon IGBTs and the state-of-the-art investigated 3.3 kV silicon carbide MOSFETs, and we have compared the converters to each other from energy storage, semiconductor, die size utilization, efficiency, and power density points of view. So this is the experimental evaluation of medium voltage silicon carbide MOSFETs. The setup is slightly modified compared to what you saw in the presentation. So we have the same bulk capacitor bank and the bleeding resistors connected to the devices with superconductor bus bars. Instead of just one silicon carbide MOSFET under test, we have two silicon carbide MOSFET half bridges, which compose a full bridge cell. There is also a 3.3 kV 1200 amp silicon IGBT for protection purposes, although the gate drivers designed have DSAT protection, but this IGBT is for upstream control and protection of the current in case of any failure on the setup. So this setup is going to be used for experimentally evaluating the 3.3 kV silicon carbide MOSFETs and also verifying the results we have achieved by simulation. Thank you very much for watching this video. I hope you find useful information in this video and also in the corresponding paper.